Hi, programming philosophers. Today I wanted to have a look into how computers really think. And for this, we have to dive into computer architecture and assembler and machine language. Inside your computer, you have a processor or central processing unit, which controls everything. Basically, think of it like a man in front of a lot of calculators and with some file cabinet on his back. So the file cabinet represents the memory, random access memory or RAM of your computer, and the calculators represent the processor registers. They can only store 64 bytes or something like that, depending on the computer architecture. And whenever this guy needs to do an operation, he looks onto one of his calculators, which point him exactly to the file cabinet place where his next order, his next machine language command stands. Then this guy increases the number and points it to the next instruction and executes the instruction. This instruction can be to fetch data from RAM onto the calculators, to do some calculation, or to write back the data to the file. There are a lot of more things that the processor can do. For example, output something to the hard disk, output something to the graphic cards, or use direct memory access of graphic card and sound card, but we come to this later. In order to understand the principle, I want you to picture the processor as a person who is unbelievably fast in calculating, has 16 calculators in front of him, and one of the calculators always shows an instruction that is in one of these file cabinets. Another one always shows where he has his memory for the current process, and there are many more calculators. And these calculators are, as I have said, the registers. Now, when, for example, the man wants to do any calculation of anything here in this file cabinet, of any data here in this file cabinet, so compare or even a comparison, then he has to fetch the data from a memory address to the calculator, perform the calculation, and send back the data to the memory address. So this is the case because in memory there is no logical unit. The only logical units are based on the registers. Okay, this sounds now like a lot of theory, and that is why I want to show you how you can quite easily under Linux demonstrate what I was just talking about. In order to do this, I have installed here Linux Mint on a little virtual box, a virtual machine, and I can surf around it here. And I have created a file calc.c, which is written in the C programming language. Excuse me. And you see this program does nothing else but create an integer, set it to 5, and then use the integer and create another integer and set it to I plus 4. So when I compile it, I translate it into machine language. So compiling is translating into machine language. And then when I disassemble it, for example, with the command objdump -d, you see this here in the section main. This is the first. This here is machine language, and here you have assembly language. Assembly language is basically a mapping so that each machine language command corresponds to one assembly command, but it is written almost as an English word, and you can almost understand what it means. So if you see in hexadecimal in the RAM F30F1EFA, that means that the command endbr will be executed. And that's actually a bad example because it does not lead us forward. Here, for example, if we look at 55 hexadecimal, that is a push. And it is a push of the register BP. BP is the base pointer, and the base pointer will then put onto the stack. Stack is in the memory. So what will happen in our example? In our example, this guy would have one of the calculators named BP, like base pointer. He would take its value and write it to the top of the stack here in the file cabinet. And where's the stack? Well, for this, you have another calculator where you look it up. And this one is called SP, like stack pointer. So by doing this, you can make a backup of your register right to the memory. That is a push command. Okay. And now let's go further. The next one is that it loads the base pointer over the stack pointer, so it makes sure that these are identical, and then it will move the long value. Long means like integer. It means that you have 4 bytes. So it will move the long value 5 into an address that is given by the base pointer. And this is how a processor works. Relatively complicated. You always have a processor, you always have a register governing where the next data is written. And here, for example, if you ask where will this value 5, to which address in memory will it be written? Then you have to first know the base pointer, the register base pointer, and then it will be written 8 bytes in front of the base pointer. And then the next thing is that it moves the value of the base pointer into the register AX. And the register AX is a general purpose register, meaning you can do with it whatever you want. You can, for example, do additions in it. And then it adds the 4 that we have seen in the source code. Okay, you remember I said in the first command int e equals 5, and in the second command int n equals I plus 4. Yeah, so it adds the plus sign mean it doesn't add. It adds the 4 and it adds it into the register AX. And then it moves this register to the base pointer -4. So if we now look at the base pointer -8, there we have 4 bytes. And these 4 bytes will represent one integer, and it is set to 5. And then at 4, we have the next integer, and this is 4. So 4 bytes left of the base pointer, we will finally find our 4. Sorry, not our 4. The result of the addition of 4 to EAX. So the result of the addition of 4 to 5. And this is how it goes on. And this is how the processor uses its registers and how it addresses its RAM. And it goes much further, because now you may ask, how does a Hello World program work? Huh? And the answer is quite easy. We write again a demo program, hello.c, and it does nothing else but printing hello world. We are using the standard IO library. We compile this as well. GCC means GNU Compiler Collection. O is for output file. And we use the hello.c file. And when we now execute this, then we see that hello world will be written. So how does it work exactly? If we have now if we have a look at this file hello, and look at everything that is human readable, for this we use the command strings. Then inside this file we will also find hello world somewhere. No? Can I find it? Yes. Here it is. This is somewhere in the file. It will get loaded into memory when hello gets executed. and it will also have an address of this string. And when we now do an object dump -d, then we see that the main function, we always have to look at the main function, because thanks to some load and low-level Linux loader shenanigans, we have a lot more here, but here's where the fun starts. So again, it starts with the command nbr, which is there for security reasons, and then it loads the effective address of the hello world into the register AX. Then and then in the end it calls printf. Printf will then have a look at at EAX, and EAX is 0, and that means that that you use the function of printf to just print out a 0 terminated string, and in DI, so in the register data indicator, there you have the address of the actual string. So let's have a look at this here. So we have data indicator. This calculator points, let's say, to this here, to this folder, and here are, and it has a number in it, and all data is numbered from 1 to 16 billion or whatever. If you have 16 gigabyte RAM. The truth is again a bit more complicated, but we come to this when we talk about swapping and virtual memory and all that stuff. But let me say it again. Here you have one calculator, one processor register that points to the data that needs to be consumed, and then you have this processor register AX, and then you call printf. Printf now looks at the register AX and sees it as 0 and knows, okay, then I have to print a string. Okay, so what do I do to print a string? I just look at the register DI. This points here, so I print out the string that starts here. We have a lot of security concerns here. For example, if you can manipulate a string so that it does not end with a 0, and then you may be able to execute arbitrary code, but that is something that comes much later. Just to give you the general idea of how a processor works, here we have one register, which is AX. It is a general purpose register. It is a signal, what shall you do if you are a function. And then you have DI for data indicator. It points right to where the data is, and in our case the data is the string hello world, and this will be put out. After this has all finished, you do a pop on the base pointer. Before, as I said, you have done a push on the base pointer, which basically means you have put the base pointer onto the stack, so you have made a backup of your register into the RAM. And now you restore this backup. So at the end of this program, the base pointer will be whatever it has been at the beginning. And this is why you use push and pop. And red just stands for return. And that means in the end that the control will be given back to the operating system. This is how a processor works roughly. It can get, of course, much more complicated, and this is where instruction sets or machine architectures come into place. So what we saw right now was the code on an Intel processor, which used to be the 8086 processor, and then later became the 8286 processor, then the 8386 processor, and much later the x64 processor. Because the 386 processor had the problem that the 386 processor had the great feature that it had 32-bit. So what happened to our clerk here in the data cabinet? You have here a data pointer, and this has only 16 bits. So what happens? you can only address 16 bits of memory, because that's the only thing that the calculator is capable of. And that means you can only address 65,536 bytes of RAM. So what did the Intel processor designers do? They had 16 byte 16-bit processor registers in their 286 processor. And then they made it incredibly complicated and had one calculator to indicate the segment of the RAM, and the next one to indicate not the segment but the individual byte of the RAM. So with 16, so you could, also all your registers were only 16-bit, you could address more than 65,536 bytes in your RAM. But not as much as 32, because these segments were overlapping. So it became incredibly complicated, and in the end, the machine was bound to 1 megabyte. It was not possible to address more than 1 megabyte of RAM. Then the E386 machine came, and it had 32 bit registers, which meant that you could address 4 gigabyte of RAM, which was already unbelievably much. And in these days, nobody could imagine that one would ever have so much RAM. But this laptop on which I'm working here has already 8 gigabyte of RAM. So we had 32-bit registers, and it became possible to address 4 gigabyte of RAM. But that was still not enough, because big enterprises need bigger computers. So people started with the 64-bit architecture, and this is why it is now called x64. So the architecture from Intel that we are now working on is now called x64 because it has 64 bits. And you just saw it in action. We had a C code that said include stdio and printf hello world. And we have looked at it, and the assembler code looked like this. It would first make a backup of the base pointer, and then do some other shenanigans, load the effective address into the register AX, move the register AX into the register data indicator, and then move 0 to the register AX, and then call printf. And printf would see, okay, AX is 0, so I have to print something. Okay, I go to data indicator, and whatever is written there, I will output onto the console. And this is how this x64 machine works. And the interesting thing is that nothing has changed, and that the same instructions were already available with an i386SX processor, which was the first processor I ever owned. And then we have the machine language. So here you have the architecture. Here you have the code in the language, in the programming language C. Here it is translated to x64 assembler, and here it is translated to x64 machine language. Note that if you compile this C code for an ARM architecture, it will look differently, because the ARM architecture is what you typically have in your mobile phone or in your Raspberry Pi or on ARM servers. And when you, as I said, when you compile this very program on the ARM architecture, then the output will look like this. And you see that it has a fixed length instruction. So each instruction is exactly 4 bytes long, which is pretty standard and pretty done by all processor architectures, with the exception of Intel. And this allows pretty much to do a good jump. Yeah, for example, if you are here and you want to jump 4 commands into the future, then you just add 16 bytes. Then you just add 16 to the processor indicator, to the, how is it called? Instruction pointer. You just add 16 to the instruction pointer, and then you will no longer be here, but 4, 8, 12, 16, then you will be here. However, Intel, for whatever reason, did not want to do it, and they decided that it would be a good idea to have short commands like for push, because you use push very often, especially push of the base pointer. There you would only need 1 byte, while for other commands you would need 4 bytes, or even in this example up to 7 bytes. And and this is how computers really internally think. They do not think in terms like, print something. They cannot do it. They can just add, move, and output something. And when we dive into this later on, we will also see how this call evaluates. So when we go, we dive very deep here. But let's dive yet a bit deeper. Let's find out how the printf command really is written. And once we have found out this, you will understand, well, in the end, your system has to access somehow the graphical memory, and to manipulate the graphical memory in some way, because you need to print something onto onto the graphic card, onto the screen. You need to print something onto the screen, and that is why you need to access the graphic card, especially the graphical memory. Yeah. Okay, so that was the absolute beginning of my rant on how computers think, and how computers think differently. Because if you look here, this is a completely different way of thinking from this here. And that means that ARM computers may be optimized for something which Intel processors are not optimized for, especially because we are using them in mobile phones. ARM computers excel at low energy consumption, while with Intel processors you just get more processing power. So I once tried to build up an NFS server on the ARM architecture with a Raspberry Pi, and that is something that should really be trivial. However, this thing was too slow for being a decent NFS server. So I gave up my project of creating an NFS server out of my Raspberry Pi. So, clear advantages of thinking differently, and this often reminds me of people who think differently. Yeah, sometimes I think, I just have another instruction set in my head than other people, especially if these other people behave differently. And this is how programming can become quite philosophical. Thanks for your attention.